Hello everybody. Today let us discuss the quicksort algorithm. Quicksort algorithm is used to arrange the elements of a given list in ascending or descending order. Like merge sort algorithm, quicksort algorithm is also based on the algorithm design technique divide and conquer, wherein the given problem is divided into smaller subproblems and the smaller subproblems are solved recursively. However, in quicksort, the smaller subproblems that are divided may not be of the same size, and secondly, once the smaller subproblems are solved, there may be no need to conquer the solutions of the smaller subproblems to get the solution to the original problem, because once the smaller subproblems are solved, the original problem will be solved. Let us understand the working principle of quicksort algorithm with an example. Let us consider we have an array of numbers which are to be sorted in the ascending order, and let us assume that this list is stored in an array named as A and the elements are in between two pointers low and high. The idea of quicksort is to select one of the elements present in the list called as the pivot element. We can select any one of the elements present in the list as the pivot and place the pivot in the list in such a position such that elements present to the left of the pivot are less than or equal to the pivot and elements present to the right of the pivot are greater than pivot. Even though we can select any one of the elements as the pivot, to keep things simple, we always select the first element present in the list as the pivot, and to achieve the partition, that is to find a position to place the pivot such that elements present to the left are smaller and right are greater, we use two pointers. One is a I pointer which is placed immediately after the pivot and another pointer, J pointer, which is placed at the end of the list. The purpose of the I pointer is to skip those elements that are smaller than the pivot. This is achieved by comparing the element pointed to by the I pointer with the pivot element, and if it is smaller, we skip the I pointer. Because quicksort requires elements smaller than the pivot be present to the left of the pivot, so therefore if we find an element smaller than the pivot, then we skip the I pointer, hoping to find a position after this smaller element to place the pivot. Once we encounter an element larger than the pivot, the I pointer stops there because the larger element can't be present to the left of the pivot, so we can't place the pivot anywhere later than the larger element. We stop there and we start with the J pointer. J pointer moves backwards, it skips the elements which are larger than the pivot. When we encounter an element smaller than the pivot, we stop because that element can't be present to the right of the pivot. Let us see how it happens. Now, the element pointed to by the I pointer 1 is smaller than the pivot. It can be present to the left of 6. So therefore, what we do is, we move the I pointer to find a position to place 6, so that 1 which is smaller than 6 will be present to the left of 6. 3 compared with 6 is smaller, therefore we increment the I pointer and we come to 7. When we compare 7 and 6, 7 happens to be greater than 6, therefore we can't skip the forward the I pointer because 7 can't be present anywhere to the left of 6. It can be present to the right of 6. We'll stop there and we will see what will happen with the J pointer. J pointer can skip elements larger than the pivot. We compare 8 with 6. 8 is greater than 6. Therefore, 8 can be present to the right of the pivot. Therefore, we decrement the J pointer to, when we compare it with 6, we find that 2 is smaller than 6. It can't be present to the right of the pivot. Therefore, J pointer stops there. So, when the I and the J pointer stop, two things can happen. One is, the I and J pointer would have crossed over, that is, I would have gone beyond J or J would have come before that of I. In which case, the value of the I pointer will be greater than that of the J pointer, and if this has happened, we have achieved the partition. A position where we can place the pivot so that elements present to the left are smaller and elements present to the right are greater. In this case, that has not happened. I is still less than J, I and J have not crossed over. Therefore, we can't place 6 anywhere in this list such that elements present to the left of 6 are smaller and right are greater. So what should we do now? One observation if we can make, I pointer stopped because it encountered an element that is larger than the pivot. This element can be present to the right of the pivot. Same way, we encountered an element 2 with the j pointer which is smaller than the pivot, which can be present to the left of the pivot but not to the right. Therefore, what we can do is we can swap the elements pointed to by the I pointer and the j pointer. Therefore, if I and j have not crossed over, what we are going to do is we are going to swap a of I and a of j, elements pointed to by the I pointer and the j pointer. We keep, after swapping, we continue what we were doing earlier, comparing the elements pointed to by the I pointer and the j pointer with the pivot and incrementing. 2, 9, 5, 7, 8. So we have swapped a of I and a of j. I pointer is still here, j pointer is still here. Okay. Again we continue the same process. 2 is compared with 6. 2 is smaller. It can be present to the left. That is the reason why we swapped. I pointer is incremented. 4 is compared with 6. 4 is smaller. It can be present to the left. I pointer is incremented. 9 is greater than 6. It can't be present to the left. We'll stop the I pointer j there and we'll come to the j pointer. 7 is greater than 6. Yes, it can be present to the right of 6. J pointer is decremented. Then we encounter 5. 5 is not greater than 6. It can't come to the right. Again we have come to the same situation wherein I and j have not crossed over. Therefore, we again swap a of I and a of j. 6 is still the pivot. 1, 3, 2, 4, 5, 9, 7, 8. I pointer is here, j pointer is here. Continue the same process. This may happen any number of times. Okay. In some cases, in the first pass, in one comparison itself, the I and j might cross over. Once we scan I and j, they may get crossed over. But in some cases it may take any number of times. Therefore, as long as I and j cross over, we need to keep doing this. That is the indication that we have found the partition. 5 is smaller than 6. Therefore, I can be incremented. 9 is not smaller than 6. Therefore, we stop I pointer. We start with the j pointer. 9 is greater than 6. Therefore, the j pointer can be decremented. 5 is not greater than 6. J also stops there. Now we can see I and j have crossed over. The value of I has become greater than j, or j's value has become lesser than I. Now we can place 6 in some position such that elements present to the left are smaller than 6 and elements present to the right are greater than 6. Which is that position? If we can observe, if we swap 6 with the element pointed to by the I pointer, that is 9, 9 happens to come to the left of 6 because 6 comes here and 9 comes here. We can't have an element larger than 6 present to the left of 6. Therefore, it is not the element pointed to by I that we can swap. We will check with element pointed to by j. 5, when it is swapped with 6, 6 comes here and 5 comes here. 5 being smaller than 6 can be present to the left of 6. So therefore, when the I and j pointers cross over, we will swap a of j and the pivot. Okay. So when we do that, 5 comes here, 1, 3, 2, 4, 6 is the pivot, 9, 7, 8. So now we can see the pivot is placed in a position in the list such that elements present to the left are less than 6, elements present to the right of 6 are greater than 6. However, the elements present in the left subarray are not sorted. Elements present in the right subarray are not sorted. We need to sort them separately using the same technique. We need to consider the left subarray separately, take this as the pivot, apply the same technique and sort these elements. Again it will be divided into 2, further it may be divided into 2. So that is how it applies the divide and conquer technique recursively and solves the left subarray. Similarly, it solves the right subarray. But one thing what we can observe is the pivot 6, when it is placed, it is its final sorted position. It will not change its position later. After you sort the left subarray and the right subarray, the position of 6 doesn't change. The pivot element, once we place, it will be placed in its final sorted position. So once we place the pivot, that is what we call as one pass of the algorithm. So after one pass, the pivot gets placed in its final sorted position in the list. Now We can also construct a tree of recursive calls, okay, for the list of elements. So here the low was at 1, high was at 9. We have, see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and where did we achieve the partition? Partition we achieved at 1, 2, 3, 4, 5, 6th position. Partition is achieved at 6. Okay, so now this has given rise to two more subproblems. One subproblem in which the left will be at 1 itself, but high will be 1 less than the partition wherever we place, that is 6 minus 1, 5. Okay, the other subproblem will be left will be 1 after the partition, that is 7, and high will be at the same position, 9. So in these two subarrays we need to find the partitions. That we will do. So we will take the left subarray, 5, 1, 3, 2, 4. Okay, 6 anyways will be there, 9, 8, 7 we'll have to do separately. We'll take this as the pivot. I pointer is pointed to 1, J pointer is pointed to 4. 1 is smaller than 5. Skip the I pointer. 3 is smaller than 5. Skip the I pointer because these two elements can be present to the left of 5. 2 is also smaller than 5. It can also be present to the left of 5. Come here. 4 is also smaller than 5. Increment the I pointer further, and now we can see I pointer has gone out of the range of this subarray because this is the subarray that we have to sort now. For us now, our low is here, high is here because low is at 1, high is at 5. This is the range that is given to us. So even though this is a valid array, for us the I pointer has gone out of the range of the array. Now we will move the J pointer. 4 is not greater than 5, therefore J pointer stops there itself. I and J have crossed over. Since they have crossed over, A of J and pivot can be swapped just like we did at the end. So now you can see one stretch I and J got crossed over. So we will swap A of J and pivot and achieve the partition. 4, 1, 3, 2, 5. So 5 is placed here. Okay. So now in the left subarray, where did the partition occur? Partition occurred at 5. And this will give rise to two subarrays. Okay. So 1 where low is at 1, high is at partition minus 1, that is 4. Okay, 1 to 4. So these 4 elements. On the right side we can see low is at partition plus 1, that is 6, and high is at 5. You can see low and high. Low has to be less than high. Only then we have some elements in between to sort. Now low has become greater than high, which means that there is nothing for us to do with the right subarray and the tree ends here. This left subarray anyways will continue because these elements have to be further sorted. So we'll take this as the pivot. I pointer, J pointer. 1 is less than 4. I get points here. 3 is less than 4. I points here. 2 is less than 4. I points here out of the range because this is the range what we have. We will try to move the J pointer. 2 is not greater than 4. 2 will remain there itself. So once again we have achieved the partition by swapping 2 and 4. 2 comes here. 1, 3, 4. Okay. So partition has occurred at 4. This has given rise to two subarrays. Low is at 1, high is at 3, and on the right side low is at 5, high is at 4. So that subarray stops there. 2 and 3. 2 is the pivot, I is here, J is here. This is the range that is available to us. 1 is less than 2, I pointer gets incremented. 3 is not less than 2, stops there. J pointer, 3 is greater than 2, so therefore J pointer gets decremented. 1 is not greater than 2, therefore J pointer stops here. Once again I and J have crossed over. Swap of J and pivot. 1, 2, 3. Pivot is placed here. Okay. So now partition has occurred at 2, position 2. Now here if you can see, low will be at 1, high also will be at 1, 2 minus 1. So therefore there is only one element left here, nothing to do, that element is sorted. Similarly, right side, low is partition plus 1, that is 3, and high is also 3, only one element. So this is sorted, this is sorted. These two elements need not be sorted. 1, 2, 3, 4, 5, 6, all of them are sorted. We'll take the right subarray, 9 as the pivot, I pointer is pointing here, j pointer is pointing here. 7 is less than 9, I gets incremented. 8 is less than 9, I gets incremented out of the range. We will start moving the j pointer. J is not greater than 9, stop there. Okay, so I and j have crossed over, swap, pivot and a of j. 8, 7, 9. Okay, so 9. So now here the partition has occurred at 9. This has given rise to two subarrays. Okay, anyways this is not there, so I erase it. One is left is at 7, low is at 7, I is at 8. Okay, 7 to 8, and right side we have left is at 10 and I is at 9. This subarray is not there. This subarray we need to find the partition. 8 is the pivot, I is placed here, j is also placed here because we have only two elements. That is the first element and that is the last element on the second element. 7 is less than 8, I pointer gets incremented. It has gone out of the range, it stops there. 7 is less than 8, therefore j doesn't move. I and j have crossed over, swap a of I and a of j and pivot. 7, 8 and 9 is there anyways here. Okay, sorted. So this has given the partition at 8. Left side we have low is at 7, high is also at 7. Okay, so this is sorted. Right side we have low is at 9, high is at 8. So therefore this subtree is not there. That is the tree of recursive calls, and we can see that all the elements are sorted now. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is how the quicksort algorithm sorts the given elements. So always it selects one of the elements, in our case the leftmost element as the pivot element, and it keeps two pointers and skips the elements smaller than the pivot from the left side and skips the elements larger than the pivot from the right side. When I and j cross over, it places the pivot by swapping pivot and the element pointed to by the j pointer. Now let us see how the algorithm for quicksort look like. The quicksort algorithm will also have two parts. One is the quicksort algorithm, which will call the partition algorithm recursively to sort the left subarray and the right subarray. The array is represented by A and it has two pointers, low and high, to define the range of the array elements. Within this we have if low is less than high. If low is less than high, then what we do is we will find the partition p is equal to, we will call another function partition function, which will return the position of the partition in the tree we wrote. In this array, in between low and high pointer, find me a partition. Once the partition is found, again I will call this quicksort algorithm recursively quicksort in the array from low to partition minus 1 is the left subarray, and the right side I have in the same array. Now I need not touch the element present at the partition, one less than that, one greater than that, because the key element pivot is placed at its final sorted position. Partition plus 1 comma high. So this is the algorithm which does the partitions recursively and calls the left subarray and the right subarray for sorting. Okay. Now we will see the partition algorithm. partition algorithm will also take the same array and the low and the high pointers. Okay, so in the partition array, first we will identify the pivot. So pivot will be the element which is pointed to by the low pointer in the array, and we place a high pointer to the element which is present next to the pivot, low plus 1, and a j pointer which will be positioned at the last location of the array. Then, as I told, we need to move the I pointer and the j pointer as long as I and j cross over. We don't know when it may happen. Therefore, we will enter an infinite loop as long as I and j pointer doesn't cross over. Okay. So now, while I is less than or less than high, the I pointer can get incremented until it goes to the end of the list, and a of I is less than or equal to pivot. What we should do, we have to increment the I pointer. Okay, as long as the element pointed by the I pointer is less than or equal to pivot, we are going to increment the I pointer. And the other case is, if it reaches high, it means that that is the last element that we can compare. If it goes beyond that, it has gone out of the range. Same way, as long as j is greater than or equal to low, because it can come one element before that of pivot. Low is placed at one element after the pivot, so even the pivot element can be considered. Sometimes the pointer stops at the pivot element, therefore j is greater than or equal to low, and a of j is greater than pivot j minus minus. Okay, we are decrementing the j pointer. So now once we this will keep happening. Okay, so if at all, if I is less than j, means I and j have not crossed over, then what we are going to do is swap elements present at the I pointer and the elements pointed to by the j pointer. Okay, if I is greater than j, then they have swapped they have crossed over. We will swap pivot with a of j. Okay, so we will return pivot with a of j, and we have achieved the partition, and therefore we will return the partition position, that is j. So j is the position where the partition has occurred, that will be returned, and with respect to that partition, the left subarray and the right subarray will be recursively sorted. Okay. So what is the efficiency of the quicksort algorithm? So quicksort's algorithm, we need to analyze in best case, worst case and average case. When does the first we'll analyze the worst case of the quicksort algorithm. When does the worst case of the quicksort algorithm occur? The worst case of quicksort occurs if the partition occurs at the end always. Meaning, in that case what happens is, whenever we place the pivot element, there will be n minus 1 elements to one side of the pivot and the other side will not have any elements at all. Okay, something like 9, 7, 8. We'll take in descending order: 8, 7, 6, 5, 4. If we take these elements, if we take 9 as the pivot first, 9 will be placed here and all these elements will be less than the pivot. Then when we take 8, 8 will be placed here and all the elements to the left will be smaller than. So the other side we will not have any elements at all. There will be zero number of elements. So this is when worst case occurs in quicksort algorithm. So if we represent C of n as the number of times the basic operation, that is the comparison operation, is performed to do the partition, then we will see how many times comparison operation will be performed. See, here we have 6 elements. Okay, when we have 6 elements, how many times are we performing the comparison to place the 6 in its final position? So I pointer will be pointed here, all these elements are smaller, so 1, 2, 3, 4, 5 comparisons will be done with respect to I, and j with respect to j 1 comparison will be done. It compares with 4 and it stops there, so totally 6 number of comparisons will be done. What can we conclude is, when there are n number of elements, the number of comparisons that will be done is n comparisons, plus after doing the comparison we will have one side of the array as it is, and that needs to be further done in the same fashion. Recursively it needs to be sorted. Okay, so as I told, the partition will happen at the end always. It can be here or it can be here. It may happen alternately also. Once the largest element happens to come here, then the smaller element happens to come here. So therefore it is like the elements in the ascending order or in the descending order, both of them will be worst case input to the quicksort algorithm, wherein either the largest element will be placed to one corner or the smallest element will be placed to other corner, and that happens in each one of the passes. So we don't know how many times this will happen. Okay, so when the number of elements is 1 less than n, because one element pivot is already placed, we are left out with n minus 1 elements. How many times we are doing, so that we don't know. Okay, and when if the number of elements is greater than 1, if the number of elements is equal to 1, then we are not going to do any comparison at all. In the tree we saw, when there is only one element, we don't do anything, we leave it because that element is already in the sorted position. So it is equal to 0. So this we need to solve. We can solve it by the method of backward substitution. C of n is equal to C of n minus 1 plus n, okay, which will give rise to C of n minus 2 plus n minus 1 plus n, because here when we have n minus 1, and 1 less than this we have 1 more than this we have here. Okay, so this will be, when it is n minus 1 here we'll have n minus 2 and here we'll have n. Okay, so same way we proceed. C of n minus 3 plus n minus 2 plus n minus 1 plus n. In this fashion we proceed when n is equal to 1. Okay, so when this proceeds and this becomes C of 0, we'll continue this till some point. n minus I is equal to n minus I plus 1 plus up to n minus 2 plus n minus 1 plus n. Okay, so now we want this to be 0, because C of 1, we had the initial condition C of 0 is equal to C of 1 is equal to 0. So therefore we need to make this as 1. If we need to make this as 1, then I value should be made as n minus I is equal to 1, means I is equal to n minus 1. So when we substitute this, we will get it as C of n minus n plus 1 plus n minus 1 plus 1 n minus 1 plus n. Okay, so this will become C of 1 plus n minus n. This will become 1 plus 1, 2 plus up to n minus 1 plus n. So it is, you can see the series, it is 2 plus 3 plus 4 plus up to n minus 1 plus n. So we have a formula for this here, 1 plus 2 plus up to n. We have a formula, n into n plus 1 by 2, which is n squared plus n by 2. So approximately n squared, therefore it belongs to theta of n squared. So the worst case of quicksort algorithm is quadratic. It belongs to the order of growth of n squared. Okay, so the worst case efficiency of quicksort is not good. It is a quadratic algorithm in the worst case. What happens to quicksort in the best case? When will the best case occur? So the best case occurs to quicksort when the partition occurs in the middle, exactly middle always. Okay, so something like, say if we have so now when 5 is placed, we will have 3 elements to the left which are smaller than 5 and 3 elements to the right which are greater than 5, and this has to happen always in each of the partitions. Just like in the worst case the partition occurs at the end always, here also the partition occurs at the middle always. Okay, so how many times we are going to do comparison over here? So here we can see I pointer is placed here, J pointer is placed here, I gets incremented, skips this 1, 2, 3, 4, it stops here. Okay, J pointer, it skips this 1, 2, 3, 4. So it does comparisons 8 number of times. Totally how many elements are there? 7 elements are there, and it does comparisons 8 times. So therefore, and after doing the comparisons 8 number of times, the pivot will be placed here. Left side we will have approximately n by 2 number of elements, and right side we will have approximately n by 2 number of elements. So therefore C of n in this particular case will be 2C of n by 2, because the array will be divided into 2 halves which consists of approximately n by 2 number of elements, and to achieve this partition we had to perform n plus 1 number of comparisons. When there were 7 elements, we performed 8 comparisons to partition the array, so n plus 1 number of comparisons. Okay, so this is the recurrence relation for best case, and if we apply Master's theorem, A is equal to 2, B is equal to 2, okay, and this is the function f of n. F of n is equal to n plus 1. It belongs to theta of n, okay, that is it belongs to theta of n to the power of d. Therefore d is equal to 1. So now we have A, we have B, we have D, and the comparison when we do, A will be equal to B to the power of D, that is 2 is equal to 2 to the power of 1, D is 1. So therefore this implies that C of n belongs to n to the power of d log n, that is it belongs to d is 1, we have got belongs to theta of n into log n. Okay, so this is the best case efficiency of quicksort algorithm. So in the best case, quicksort algorithm belongs to the efficiency class n log n. Average case analysis, we need to consider the possibility of the partition happening at each and every places. Anyway, it is not a very simple method to do the average case analysis, but the average case analysis of quicksort is also n log n. So in best case and in average case, quicksort belongs to n log n efficiency class, and in worst case it is quadratic. However, practical applications have shown that quicksort algorithm performs better, because the input can either be 2 worst or 2 best. So therefore, on an average, practical applications quicksort algorithm performs better than other sorting algorithms. Thank you.